So yesterday we talked about how to multiply and divide complex numbers that are in polar form. It stands to reason that we want to talk about what are the other operations that we can do to numbers. So today we're going to talk about how we find powers or use exponents on complex numbers and their exact opposites. How do I find the roots, or how do I take a radical of a complex number? Let's start off by recapping what we talked about yesterday. Yesterday we talked about ways to multiply and divide. I didn't give these guys a name. Let's just call it the multiplication and division rules of complex numbers in polar form. So yesterday we saw that for any two complex numbers in polar form, so let's say z sub 1, if it's in polar form, it has a modulus r sub 1 and an argument theta sub 1. Z sub 2, same format, but with subscripts 2. So here we have two complex numbers in polar form. We should know that if we wanted to multiply these two complex numbers, all you have to do is multiply their modulus and add their arguments, add their angles. If I wanted to divide these complex numbers, all you have to do is divide the modulus and subtract the arguments. So that's what we talked about yesterday. And again, this might be a good recap of yesterday's, not plural. This might be something good to highlight, box, add to your index card if you have one. So the idea of exponents, using exponents in complex numbers, is just an application of what we talked about yesterday, because we should know, just by how regular numbers work, that exponents is just repeated multiplication. So the idea, we're just going to borrow from regular arithmetic. Exponentiation may be thought of as repeated multiplication. For example, in the regular number system, 5 cubed, what does that mean? Well, that just means 5 times 5 times 5. Therefore, if I had a complex number, say z cubed, that's just the complex number times the complex number times the complex number again. So, if we had a complex number, z sub 1, I'm going to drop the subscript since I'm only going to deal with one of them. So if I have a complex number in polar form, z equals r cosine theta plus I sine theta, wouldn't z squared just be z times z? And of course, using the multiplication rule that we came up with yesterday, that means we just multiply the r's together. So r times r is r squared. And then we add the angles together. Well, theta plus theta is 2 thetas. Well, what about z cubed? Well, that's z times z times z, right? Or in other words, z times z squared. Well, you multiply the modulus together. So r squared times r is r cubed. And then you add the angles or the arguments together. 2 theta plus theta is 3 theta. And I hope you guys see a pattern forming. If you have a single single complex number, z to the first power, you have a single r and single thetas. If you have z squared, you have r squared and 2 thetas. If you have, let's see if this color will show, z cubed, you have r cubed and 3 thetas. So I hope, ... by patterns, we can see that z to the fourth, you'd have the fourth power on the r, and 4 times theta. If you had z to the 5, you'd have r to the 5th power times cosine of 5 thetas, and so forth. This observation, this pattern, is called DeMoivre's theorem, or DeMoivre's theorem. I'm not good at pronouncing French, so pronounce it however you want. But DeMoivre's theorem, or DeMoivre's theorem, gives us a way to exponentiate or apply an exponent to a complex number in polar form. It states that if z equals r cosine theta plus I sine theta, then for any integer, so it works for positive whole numbers or negative whole numbers, for any integer n, if I raise that complex number z to the nth power, all I have to do is apply the exponent to the modulus and multiply the angle by the n. So this is the formula, or this is the way that we would apply an exponent to complex numbers. And it can be helpful when it comes to exponentiating complex numbers to high exponents. So for example, if I asked you to evaluate or find, let's make an ugly complex number. Let's use fractions. 1/2 plus 1/2 I to the 10th power. Now, back in Unit 10, what would this entail? This would entail you writing, 1/2 plus 1/2 I times 1/2 plus 1/2 I, ... 10 times, repeated distribution. That is, I wouldn't even bother trying to start that. That is a pain in the butt. So you can see this is where polar form of complex numbers really shine, because if, and this is a big if we can represent this complex number into polar form, then DeMoivre's theorem unlocks, and we can just apply this simple concept. And of course, we should be able to write this complex number in polar form. That's what yesterday was all about. So the first thing I would do is I'm going to just define z as my complex number. Therefore, we should be able to find r and theta really quickly. So r, again, is the square roots of a squared plus b squared. So what's that? That's 1/4 plus 1/4 is 2/4. And when you apply a radical to a fraction, you can do the radical to the numerator and denominator separately. So you have radical 2 over, and the square root of 4 is just 2. So here we have r being square root of 2 over 2. And then tangent of theta is b over a. So tangent of theta equals 1. I'm not going to bother with the reference angle because I know that 1 is positive, so it'll be in the first quadrant. Theta equals pi/4. So all of this work tells us that our original number, z, is r times cosine theta plus I sine theta. So we now have successfully converted our complex number. We've converted this complex number into polar form. So now we should be able to figure out the power. So all of this work says 1/2 plus 1/2 I equals, how should I write this? Okay, let's do this. So this here is radical 2 over 2 cosine pi/4 plus I sine pi/4. Therefore, 1/2 plus 1/2 I to the 10th power equals, according to DeMoivre's theorem, you raise the r to the same exponent, and then you multiply the angle by the exponent. Right? So this is just applying DeMoivre's theorem. So you can see that when you raise a complex number to an exponent, if you have it in polar form, which we do here, you raise the modulus to the same exponent, and then you multiply the angle by the exponent. Now, there's still some more math to do. You're not done yet, but I hope this is a lot easier to work with than writing this out 10 times and doing repeated distribution for all of them. So the rest is just a little bit of arithmetic here. So radical 2 halves the 10th power. So the radical and the 10 will cancel out. So that's 2 to the 5th power or 2 to the 10th power. And then just do multiplication. So 10 pi fourths, what's that reduced to? That's 5 pi halves plus I sine 5 pi halves. Properties of exponents. So this is 1 over 2 to the 5th power. Cosine of 5 pi halves plus I sine 5 pi halves. So this is the answer in polar form. But my rule of thumb is whatever form they give it to you in, you should put your final answer in that form. So if we go to the original problem, technically the original problem, they gave it to us in standard form. So I should probably write my final answer in standard form. So again, to write your answer in standard form, you just evaluate it. Just do it. Figure out what these guys are, and then finally distribute in the modulus. So we have 1 over 2 to the 5th. That's, what's that, 1 over 32. Now, fortunately, 5 pi halves, these guys are special unit circle angles, so I expect everyone to understand and know what they are. So cosine of 5 pi halves is 0, plus sine of 5 pi halves, that is 1, so that's I. So this guy equals 1 over 32I. Pretty cool. Easy way to find exponents of big exponents of complex numbers. So pick your poison. Do you want to write this guy out 10 times and then do all that repeated distribution? Or do you want to find the polar form, which, you know, it's not that hard, not that a lot of work. And then DeMoivre's theorem makes cake work out of exponentiations. So that's it. That's how you find exponents of complex numbers. Put them in polar form first, and then DeMoivre's theorem makes exponentiations a piece of cake. Going the other direction, that's where there's a little bit of thinking involved. Now, I'm going to do things backwards. Normally we prove the idea first, and then we write the summary statement. I'm going to write the summary statement first because I think it's easier to explain from the finished product. So this is the block that I would highlight, I would stand out for my notes, I would write in my index card. The nth roots of complex numbers. Just follow with me, just write it out. It's going to look really weird and funky. We'll explain what each part means. So here's the formal statement. If we have a complex number z in polar form, which is r times cosine theta plus I sine theta, and n is a positive integer, then z has n distinct roots based upon the following formula. We'll define the roots as w, so w sub k equals r to the 1 over n times cosine of theta plus 2 pi k over n plus I sine theta plus 2 pi k over n, where k is 0, 1, 2, so on and so forth until you reach one less number than your nth root. So take some time, pause the video if you want to just digest what all of this says. But it actually looks more complicated than it really means. So let's break it down as to why this is the way it is. This formula, or this idea to find the nth root of complex numbers, is just basically DeMoivre's theorem, but in the opposite direction. What does DeMoivre's theorem say? If we exponentiate, if we apply a big exponent on a complex number, you raise the modulus by that exponent, and then you multiply the angle, the argument by the exponent. So it stands to reason, based upon sort of like the polarity of mathematics, doing the opposite. What's the opposite of exponents? It's a root or a radical. So it stands to reason, if I take a radical of a complex number, you have to take a radical of the modulus, and instead of multiplying the angles, you would divide the angles. So that's exactly what the first part of the formula says. It's the exact opposite of DeMoivre's theorem. If I have a complex number in polar form, if I want to take a radical of that complex number, we first have to take a radical of the modulus, and you guys have to remember, when you take a nth roots of a number, that's the same thing as raising that number to 1 over n. So they just wrote it in exponential form rather than radical form. So again, it's the opposite to DeMoivre's theorem. If I take a root or a radical of a complex number, instead of exponentiations, you take the radical of the modulus, and then instead of multiplying, you divide the angle by the radical. Now, what about this extra plus 2 pi k business and all of this stuff? Well, remember the fundamental theorem of algebra states, whatever the degree of your problem is, that's how many answers you should have. So, for example, you don't have to write this down in your notes. If you had x to the 7th equals 12, you would take the 7th roots. We should have, in theory, 7 different answers because the degree was 7. Now, up until now, we've only really been working in the real number system, which is why whenever we take radicals, we always got 1 or 2 answers, depending on if the roots was even or odd. But since we're expanding our minds to the complex number system, applying the fundamental theorem of algebra to the complex number system, we should be able to generate, or we need to find all of the roots. Now, where do these separate answers, or where do these other answers come from? Well, remember that since we are looking at complex numbers not based off of horizontal and vertical motions, but rather angular motions, we know that angles are infinite and they wrap around themselves within a circle. Remember back in Unit 5 when we talked about angles, we talked about this thing called coterminal angles. For example, 30 degrees is similar to 390 degrees, right? They are 2 different angles because they're 2 different numbers, but visually they are basically the same. So this is 30 degrees. This is 390 degrees. If I were to remove the labels, you would say that, they're basically visually the same angle. So that's why we have to do this plus 2 pi k business, is because if we want to generate more answers, you have to use all the coterminal angles. And to create coterminal angles, you have to add multiples of full circles, or in other words, multiples of 2 pi. Now, we want to generate distinct or unique answers. So that's why we always have to add, starting from 0, 0 2 pi's, 1 2 pi's, 2 2 pi's, all the way up to one number less than what you're dividing by. Because if you change this k to an n, these n's will just simply cancel out and you're back to where you started. So this restriction here, this sort of domain, guarantees that we will always get unique, distinct answers. So that's sort of like the explanation or the boil down of why this formula is the way it is. It's gonna be weird looking at first, but just like with everything in math, it'll only, you'll get more comfortable with it the more you use it. So let's just dive into an example here. So suppose I asked you to find all, that's the key there, find all 6 sixth roots of z equals negative 64. In other words, solve, since the textbook uses w, I'll use w. Solve w to the 6th power equals negative 64. That's basically, this set of instructions is analogous or equivalent to this set of instructions. Right. So, okay, naturally what I want to do is find the sixth root of negative 64. The first thing we need to do is convert it to polar form. Remember, all of these ideas here, DeMoivre's theorem and nth roots of complex numbers, they only work in polar form. Oops, that's not what I wanted to do. Let's move them back. There we go. They only work in polar form, so I got to first convert everything to polar form. Now, this should be a cinch. If z equals negative 64, right? Remember, everything's in standard form, so that's the same thing as negative 64 plus 0i. I hope it doesn't take a lot of thought process to know that r is 64 and theta is, what's that? Pi radians. Now, how did I do that without writing any math down? Did I do Pythagoras' theorem and the inverse tangent really quickly in my mind? No. Here's a little quick trick. If you ever had to convert any complex number that's on the axes, right? If you had to convert any pure real number or any pure imaginary number, just look at it. So if I were to plot or graph negative 64, I hope everyone agrees, real, imaginary, that negative 64 is right here. Right? R, by definition, is the distance from the origin. So what is this length here? I hope, that's pretty easy to see. That length is 64, so that's my r. And what's my angle? Well, since it's on the x-axis, since it's on the negative x-axis, I hope everyone can see that that's pi. So yeah, I sort of like, I'm not a genius. I didn't figure this out immediately in my mind. I was just able to visualize it and write down the components. So all of this says is z equals r, which is 64, times cosine of pi plus I sine pi. So I've converted my number into polar form. So let's apply the formula for the nth root of the complex numbers. So what are the six? I should have six. What are the sixth roots of z? Well, we have w sub naught, w sub 0. Actually, I'm going to go ahead and rewrite it just so I don't have to constantly scroll up and down, up and down. So let's copy and paste this guy here. We're going to, I think this is copy. Yep. And then we'll go ahead and, oops, no, this was copy. Oops, I didn't copy it correctly. And all the time I'm fussing with copy and pasting, might have been faster just to rewrite it. I think that's copy. Yeah. That's paste. Oh, crud. I don't know what oh, here we go. Why is it over there? Okay. So just as a quick reminder, let's remember the formula. I'm going to change the color to blue. There we go. So remember, this is the formula. Okay. So let's find the six roots. W, let's make all the k's into 0. W sub 0 equals r, which is 64. Raised to this, since I'm doing the sixth root, it'll be 1/6 times cosine of theta, which is pi, plus 2 pi times 0 over 6 plus I sine, same thing, pi plus 2 pi times 0 over 6. So that is the first root. And then basically what you do is you simplify and rinse and repeat the process. So the sixth root of 64 is 2. Obviously this is going to be 0, so you're left with pi 6. So 2 times cosine of pi 6 plus I sine pi 6. And if you wanted it in standard form, you just go ahead and evaluate it. Because these guys are special unit circle angles, I expect you guys to be able to figure out the standard form. So that's going to give you, what, radical 3 plus I. W sub 1, so that's the first root. W sub 1, you have 64 to the 1/6 power. cosine of pi plus 2 pi times 1 over 6 plus I sine pi plus 2 pi times 1 over 6. So notice all we did was we basically wrote the same thing, right? Except the zeros became a 1, right? And then you evaluate it. Just do the math. So 64 to the 1/6 power is 2. Cosine. All the stuff here is what? That's 3 pi over 6, which is pi halves. So that's the second root in polar form. But if you want to convert to standard form, that's pretty easy. Just evaluate it. That's going to give you 2i. So hopefully you guys get the idea. So feel free to finish this before I do. I'm going to be taking it slow instead and explaining it out. If you're still iffy what we're doing, just follow along. Hopefully you pick up the pattern. So w sub 2 is 64 to the 1/6 power. Change all the k's into 2. Cosine of pi plus 2 pi times 2 over 6 plus I sine pi plus 2 pi over 2 over 6. So that's going to give you a 2. Cosine of, that's 5 pi over 6 plus I sine 5 pi over 6. Which, if you were to evaluate it, is negative radical 3 plus I think. Yeah. W sub 3, 64 to the 1/6 power. Cosine of pi plus 2 pi times 3 over 6 plus I sine pi plus 2 pi over times 3 over 6. Which is 2. That's always going to be a 2. Cosines, that's 7 pi over 6 plus I sine 7 pi over 6. It's not squiggles because these are special unit circle angles, and that is going to give you negative radical 3 minus I. W sub 4, 64 to the 1/6 power times cosine of pi plus 2 pi thirds over 6 plus I sine pi plus 2 pi. Oh, this should be a 4, not a 3. Sorry, 4, because we're doing the k equals 4 here. Over 6. Which simplifies to, what's that? That's 2 again. Why do I even think? Because it's always going to be a 2. Cosine of 8 pi plus 1 pi is 9 pi over 6, which reduces to, was that 3 pi halves? 3 pi halves plus I sine 3 pi halves. Which, if you were to do standard form, evaluate it, that gives you negative 2i. W sub 5 equals 64 to the 1/6 power. Cosine of pi plus 2 pi times 5 over 6 plus I sine pi plus 2 pi 5 over 6, which is 2. Cosine, that's 11 pi 6 plus I sine 11 pi 6. Which, of course, if you're to find the standard form, since that's a special angle, I expect you know how to do that. That's radical 3 minus I. Now, how many answers do we have here? We have 1, 2, 3, 4, 5, and 6. So that should complete it. I don't need to do it any further. And that's sort of where this k equals 0, 1, 2, blah, 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 all the way to n minus 1 means. We were finding the 6th root. So we go up to k equals 5. So notice how I knew that we were done because this was k equals 5. You always stop one number less than whatever radical you're solving for. But let's just say for fun you forget and you did do w sub 6, right? it's not going to give you the wrong answer. What happens is you're just going to cycle through all of these answers over again. So if you were to do w sub 6, you're going to find out that it's going to give you this answer all over again. And if you did w sub 7, it'll be this answer. W sub 8, it'd be this answer, so on and so forth. So these are the 6 distinct roots. Okay. So, I mean, it's not hard. It's just following the formula. But sometimes if the roots are big, it is a bit of work. But hey, hard work never hurt. Just for fun, I'm not going to do this. I'm not going to spoil the surprise. I'm going to let you figure it out. For fun, plot the roots on a complex plane and see if you notice anything. Since we did find the standard form of all the answers, plot it. Plot it on an Argand plane. Plot it on the complex plane. And do you notice just see if you notice a pattern, right? Obviously, with radical 3 plus i's, if your coordinates has radicals in it, you're going to have to approximate. But, just see what it looks like. You'll hopefully notice something pretty neat and interesting. But that's it. That concludes 8.3. This is how you exponentiate and take radicals of complex numbers. To exponentiate, it's DeMoivre's theorem. Very, very easy concept. To exponentiate complex numbers, apply the exponent to the r and multiply the angle by the exponent. To find the complex roots of a complex number, take the radical of the r and then divide the angle. However, you have to find all of the roots by doing this plus 2 pi k business. It's going to seem complicated and messy at the beginning, but I promise you all it takes is just practice and you'll get the hang of it. So good luck.